in for session 2 for Marianne. So thanks, Alan.
Okay, we'll take the questions at the end of the three of the first 3 talks. So thank you very much, Sally. And I am just trying to. Okay, right. Peter, over to you.
Great. Thanks, Anne-Maria, and thanks, Sally. Okay, so next up is Andy Swift. And Andy is a radiologist in Sheffield, from Sheffield University, with a specialist interest in digital imaging technology for heart and lung assessments. His research group is primarily funded by the Wellcome Trust and the NIHR, and has become very focused on the development of AI tools to improve imaging assessments of patients with heart and lung disease. So over to you, Andy.
Thanks, Peter, for that introduction. I'll just try and share my screen and see what happens. Just shout out when you can see the presentation.
Yeah, that looks good. So
okay,
view.
Marvelous, that's great. Okay, so yeah, my talk's on the collaboration between AI developers and radiologists from a radiologist perspective. So thanks very much to Peter and Anna-Maria for the invitation to speak today. Obviously, AI in healthcare is a very exciting area, and I think anything that has the potential to make big changes in healthcare throws up lots of issues, patient, hospital, and even societal level. And greatly appreciate the work of Peter and Anna-Maria that they're doing here to explore this in great detail. And also, it was really great to hear the previous talk from Sally Wyatt. It's really fascinating stuff, and it's reassuring to know people are working hard and considering the ethical aspects of AI technology development. So it's not just all left up to us in the hospital to decide what we can and can't do. So I'm going to focus on my personal experience of AI in radiology, and I hope this provides some examples of collaborations that can occur between AI experts and clinicians or radiologists in hospitals, and it shows that there's usually more than 2 parties involved in any process that occurs. And also should caveat that my experiences are focused on developing new imaging technology and make better use of scans that patients undergo, but hopefully some of the general ideas will be more widely applicable. So first slide, as has kind of would have been alluded to, that there's a lot of hype around artificial intelligence, and what's the overarching motivation and ambition as imaging technology has improved, the potential useful information from scans has also increased, and as such the demand on imaging services has also increased. The demand for what clinicians want from radiology reports is increasing as the growing literature of more and more measurements that can be potentially useful makes the reports potentially more lengthy and makes it not really deliverable. So traditional radiologists traditionally radiologists will provide variable but often very short qualitative reports on scans from a CT or an MRI scan, for instance. There might be gigabytes of data in the images, but our reports will only be a couple of lines, and we don't always provide all that information that is potentially been proven in the literature to be useful, because it's just not practical. It's not possible to do that. So this is just an example slide of a deep neural network, and we may all be familiar with the instance of Google can recognize what a cat looks like compared to a dog. Deep learning with convolutional neural network is shown in this image. The approach has led to great excitement in the field and with the potential of highly accurate predictions. So the process starts with labeled information, so a label of a cat or a dog, series of images with those labels, and then the learning occurs in the deeper layers, and ultimately a model is developed that can differentiate the two animals. But I'd say here, and this is kind of applicable to what we do, the result is only ever as good as the data that has been fed into the model. So if some type of cat or dog that hasn't been included in the training sets is in a validation set, then they lead to misclassification potentially. And there's the kind of kind of idea that you put rubbish in and you get rubbish out. So that's really, you know, at the heart of partly why we haven't seen such great transition, because things can work very well in a very well defined cohort, but then you take it into a different cohort, whatever that may be, and there's more challenges there. Also, one issue is how to unravel why the AI has made a certain decision. The deeper layers of the network are traditionally considered to be a black box. However, there are some ways of getting an idea where the important features are in the image, even from the deep learning, but it is difficult to say exactly why a certain decision has been made, and hence the sort of the difficulty with the black box sort of nature of it. And I think just briefly on this is to say, I think we've been through that very big peak now of overinflated expectations, and also overinflated concerns about us losing all our jobs. So I think most of us have still got jobs, and also I don't think that most of us feel as helped out by AI as we were hoping it'd be at this stage. So maybe we're just coming out of the trough of disillusionment and into the plateau of productivity, because as you can see, there's a lot of companies around the country who are working on AI in medical imaging. This slide's taken from a radiologist who does a lot of work with regulation, Hugh Harvey, in AI, and there's a great deal of investment going into artificial intelligence, and there's a lot of work being done by the companies which we might not be fully aware of. So I think there's a lot of emerging technology which will definitely have benefits in the not too distant future. So this talk was about collaboration. So I just wanted to sort of describe in our setting of using imaging to make better use of imaging with AI, what collaborations are required, even in this very niche area. So it starts with the data from the patients, and I've been generally working in the environment where we're looking at patients' scans in a retrospective fashion. So patients who've already come through a clinical service and have their scans taken. Our approach is to use anonymized scan data. All the patient information is stripped out from the images, which is largely done by Stephen Wood, or Woody, and Pete Metherall, who are the top two characters in this little circle, ellipse, sorry. And that data is then moved into the university. Martin Brook is helping us with that a great deal. And the data and work is covered by research and development approvals, which is in another department, research and development department, and Lisa Watson is the main contact at the moment. So even within the data, there's actually quite a lot of people required for doing that. There's growing amount of AI imaging expertise in-house in our centre, Sheffield University, with Haiping Liu, Joanna Uthoff, and Lawrence Shobbs in the computer science department, and others. And then in the NHS as well. So in the NHS, there's within our Sheffield 3D lab, we have people like Pete Metherall and Michael Sharkey and others who are experienced in developing AI potential clinical applications. So there is expertise in both the university and the hospital environment, in addition to reliance on companies assisting us with development. Radiologists and imaging expertise, we have quite a lot of interested radiologists. I think everyone's aware that this big wave of artificial intelligence is supposed to be coming, so everyone's sort of engaged in the process and keen to be involved in the process as it comes along. Where our role really is to identify those clinical problems where it's most beneficial to use artificial intelligence, because not everything requires an artificial intelligence solution necessarily. Understanding the imaging acquisition. So we have physicists such as Jim Wild, how the images are acquired, the findings, and also people to make lots of measurements, and one of the and to label the data. But one of the biggest things we need to do is, for instance, if you want to be able to differentiate a cat and a dog, you need to give it lots of cats and dogs. So we have to give lots of image labeled data, lots of measurements in order to make successful algorithms. There are many clinicians growing. David Kiley leads the pulmonary hypertension unit, and we had Pankaj Garg as well with us, who was very keen on cardiac imaging with artificial intelligence. We have numerous external collaborators, and I'll come on to talk about a few of them later, some in industry, some in research groups. We work with the University of Sheffield Healthcare Gateway, and Sue Smith and Alex Wilkinson help with our project management and also assist with how we might commercialize the software going forward. If that was the way you wanted to do it, we need to know what the approaches are, how we can deliver the technology to a wider audience. And most importantly, we do work with patients. So we have Carl Burgess has worked with us previously on imaging projects and is a co-applicant on our latest artificial intelligence NIHR and AI award. And also we work with the cardiovascular patient panel. And we're exploring some of the questions around artificial intelligence, the ethical implications and things as we go through some of these projects. So what's the general outlook like? I think the likely trajectory of AI has the potential to surpass humans in the future in some tasks. I already see examples of this, which you can talk about later in the talk, where the results from the AI are potentially better, but in selected circumstances. So to give an example of a radiology trainee, someone will come into the radiology training scheme with very little experience of the imaging appearances that we then over their 5-year training, they will see lots and lots of scans, and they will get better and better and have seen more and more scans. It's the same with artificial intelligence, where we show the artificial intelligence more and more what these scans look like, and it starts to get better. So imagine after 5 years of training, a radiologist will have seen thousands and thousands of cases and seen a great deal of variation across the broad different types of scans. And until the AI has seen that amount, it can't possibly exceed the human ability, and also our ability to reason around the scan of all the different potential eventualities, and the clinical context is not known by the artificial intelligence. So we have some advantages still, fortunately. So in terms of our specific motivation in our group, MRI and CT scans, the kind of cross-sectional imaging modalities, are key investigations in the diagnosis and assessment of multiple cardiac pulmonary conditions. There is great variability in the imaging appearances of the conditions and variability in how we make measurements. The measurements are often time-consuming, and we know that there's quite a lot of human error. As I've described, there's a massive amount of unused data that could be extracted by AI. We tend to only utilize a small fraction of that data. So an automatic, unbiased, interpretable assessment that utilizes more of the data is really desirable. So we did mention about pulmonary hypertension being part of this project. So I thought I'd just show what pulmonary hypertension looks like on a couple of scans. So this is a cardiac MRI scan sliced through the 4 chambers of the heart. The chamber at the top, we've got the right ventricle, which is the front of the chest, and then just behind that we've got the right atrium. Here we go. The right ventricle, right atrium, and the left ventricle and left atrium are usually the bigger chambers in the heart, actually. So perhaps I should have shown a normal first, but so the right ventricle and right atrium become dilated, and we get tricuspid regurgitant jets, right ventricular hypertrophy, and these are features which typically occur. And then on the short axis images, you can see the right ventricle's dilated. It's flattening the septum, left ventricle, the septal deviation, right ventricular hypertrophy, and the front and the back of the chest. So this was in left lung and some of the features. So just to show you, because I'm going to show some pictures, and I thought if I just show you the pictures, you might not then, at least you've seen roughly what the scans look like. So drawing and coloring is really what we do in radiology. We spend a lot of time drawing circles. We like drawing circles, different colors, something that keeps us entertained. So in some ways, our job is a bit similar to what my daughter does at school a lot of the time. And I think we want AI to be able to replace a lot of our labor in terms of these drawings that we do. And I think getting deep learning to make drawings has great potential. And particularly if the output of the machine learning can be something that we can visually interrogate, such as one of these drawings that we currently make, then we have some kind of oversight over the machine learning. It's not saying this person has this condition, this person's going to survive for this long. It's saying, here's a drawing, you can look at it and tell us if you like it. One of the potential limitations, as we have discussed and has been discussed by others a few times, is as we get more used to the machine doing these types of drawing, do we then lose some of our skill? A bit like with map reading in Google Maps, I have no idea how to read a map anymore, because I just speak to Google and tell it where I want to go. So there's a potential loss of skill, and that needs to be addressed as we go forward. So in terms of how we do the machine learning, we're trying to leverage both human and machine intelligence using a human in the loop approach in some aspects of our work. In this example, you can see these short axis images, and the process begins with deep learning, convolutional neural network algorithms that we know to be suboptimal. And when we have experts who make edits to the contours on diverse groups of scans with different severity, etc., and then we can produce a new algorithm which is improved. And you can see as we step down, these images look a little bit nicer, the contours look a little bit nicer, and also the volume over time information which can be derived, because we're generating a volume in every phase of the cardiac cycle on these images. And you can see that over time, with more training, both the images look nicer, and also the volume time information is improved. So that's the kind of human in the loop philosophy. It's also time effective. So if we draw in 200 cases, instead of then redrawing from scratch in another 200 cases, we get the machine to run the algorithm into the next 200, and we just make some edits, and it's the edited contours that are fed back in. It means that you can potentially work out where the machine is getting it wrong and target those areas, rather than keep on drawing masses and masses, because it is very time consuming. And Samir Alabed and Kavita can attest to that. Myself, we've made over 128,000 contours on some of these short axis images, with a bit of help from some tools within the software. And these images are actually fully automated assessments of these short axis images. So the machine has automatically drawn these contours on the hearts, and the one on the left is a patient who's quite normal, with a normal looking right and left ventricle, roughly even in size. The left ventricle looks nice and round, whereas in the pulmonary hypertension, the moderate PH case, the right ventricle is much bigger. And usually, and with a lot of the existing algorithms that are emerging, this type of patient would fail in their software. It would often fail in their software because they haven't had these types of scans in their training. But it's very promising. We also, I said, we like color. We like coloring in. So bringing some color back into the black and white world of radiology is good. Here we use a threshold analysis to pick up all the little bits of muscle within the chamber, and we're doing this, again with Samir Alabed and Kavita, and with Rob van der Geest, who I haven't really introduced, but he's our collaborator in Leiden, who is a machine learning expert. On to the next slide. So just to briefly show, I don't think all those will play, they should play, but we can also look at the different types of slices that we've got. And the advantage of this is, if we can deep learn the contours on these different slices, we can build up a more accurate model of the heart, rather than reliant on one particular acquisition. So we've run the model in larger cohorts and shown that the model fails in less than about 2% of cases. And usually this is because there's quite a bit of artifact or something unusual. And we just did a rough calculation before this, and to have manually drawn all of those contours, it would take one human a whole year working full time to have analyzed all those cases. And it took the machine a couple of days. And to be honest, I think it's in some of the contours, it's slightly smoother in terms of the images, and that time the machine could be cut down even further, because with the increasing computer power, it could be cut down. So it's a clear advantage to do such tasks, such manual tasks as making segmentations. Now some software packages are already offering these types of types of approaches. And we already are using an AI approach from Medis, one of the software companies. It's actually Rob van der Geest who generated that initial algorithm that went into Medis. And as he says himself, his algorithm is now a lot better than the algorithm that we're using in Medis. And well, Medis themselves are also all the software companies have their own teams of people trying to improve their algorithms which they're using. So yeah, and a real challenge is taking the new developments to patients rapidly, finding the optimal translational commercial strategies to benefit patients as fast as possible. On CT, so CT is even more common test than MRI in the thorax. CT pulmonary angiography is one of the commonest tests in radiology departments. Anyone who has a suspected pulmonary embolism will get that and more coming through A&E. There's increased reliance on this type of imaging because it's accurate and it's fast. It's good for patients coming through A&E, etc. And through the AI Health and Care Award we're developing an automatic 4-chamber and great vessel segmentation. We intend to use using the human in loop approach to further refine that. I've been really amazed by the results. Even after the first training run, Michael Sharkey, who works in the hospitals now, we've stolen him to do some work within the university to develop this technology and other technologies. The drawings that we did manually to base this off were very time consuming and very painful. But it's been amazing to see how effective these. So essentially what you're seeing is just colored in parts of the heart fully automatically. So there's been no manual input into these drawings. And for instance, I think this has implications for general reporting, for screening. If the technology can run in the background and can flag, have you considered this person might have a dilated aorta, or is the right ventricle dilated? Would you care to just check that again, just as a backup, as a kind of fail-safe? I think there's definitely advantages there. In addition to being able to make a lot of these more complicated measurements that we don't have time to make, we don't have time to draw around the volume of the chambers in the working practice and get these measurements, which could be more useful for saying if a person potentially in some instances needs to stay in hospital, or whether they would benefit from a certain type of treatment. Also, just to say that the heart and the lungs are fairly close together in the thorax, and they're both seen on thoracic scans. So we have parallel research streams in artificial intelligence for the lung. We collaborate with Vida Diagnostics in Iowa, and also the research team in Iowa. And we're generating our own Sheffield-based pipelines for drawing and potentially training algorithms to assess the lungs. Crit Dravidi is a radiologist in Sheffield working in this area, and Joanna Hoff, postdoc, who's come from Iowa, and Michael Sharkey are working on these aspects. So our vision, I think, in general for this kind of thoracic reporting is to develop a comprehensive and automatic, reliable assessment of the heart and lungs on routine imaging investigations, taking scans that would be done routinely and making better use of them, essentially. There's some obstacles to generalizability, different patient populations, different scanner types, scan acquisition protocols, then how we roll the technology out to benefit the maximum number of patients with this type of technology is also a challenge, because if you sell some software to one particular, or you work with one particular company, they might only have a certain reach over the population. So it's how best to do this is something that we're considering. We've previously developed models based on us making manual measurements here and there in the images to make predictions, so to make a diagnosis or show that has prognostic value. These are kind of measurements that we're planning to replicate. And for instance, the black line in the bottom left-hand image shows a CT-based model that can diagnose pulmonary hypertension, and the bottom right-hand image shows that the prognostic significance with an optimal parameter threshold, and the upper line shows the patients having ideal survival who don't have the condition automatically identified. So I wanted to touch base on this additional collaboration. So outside of our immediate kind of research group, we've started collaborating with this very glamorous couple from Singapore, James Hare who's founded a sort of, I think, £1 billion tech company, and eminent cardiologist, Carolyn Lamb, who together have developed an automatic way of assessing echocardiography images. Echocardiography is really the workhorse of imaging in cardiology. So it's a very, very common test, and they've got a good tool there to make automatic measurements and predictions from the echocardiogram scans. And our relationship there is that we can potentially, it hasn't started yet, but we can potentially support them by providing a relevant clinical cohort for them to evaluate in an anonymized database, and they can then use that to develop their technology. So it's not all about us developing our own technology and taking forward. There are opportunities for others to benefit from the types of patients that we have. And I think most centers, certainly most large centers, will have certain specialist areas where they have the patients being referred from other centers. So they have the best opportunity to prove certain clinical tools for making clinical value in different settings. I wanted to touch base on another approach that we're using in Sheffield, which is to not use deep learning, which is a very popular thing to do, is deep learning, but we're using a single layered approach, which can be considered analogous to linear regression of the pixels, and it uses the tensors in the image, and then you can make it more interpretable. And I'll just show you some images of this, and it's Haiping Liu, who's the brain behind the development of this technology. And you can see here that the machine has automatically been able to draw on the image where it's found the differences between this instance patients with and without pulmonary hypertension. So it's a really interpretable type machine learning approach. And here we have the features which represent a normality. So not using deep learning has some advantages in that and also it has high diagnostic accuracy as well. We don't get into the trouble so much with in terms of that, how the machine has made a certain decision, particularly for making predictions and diagnosis. So really, to conclude, there's promising use of deep learning technology coming, potential to analyze, replicate some of the more lower level tasks that we do, such as measurements, I think is very important. Automate more time-consuming measurements, I think, is good. Save us time, improve repeatability, and improving diagnosis and prognostication is something we want to try and show in the future. And just to finish off on the same slide, really, as the beginning, is just our collaborations and kind of acknowledgements particularly from an imaging point of view. So thank you very much.
Brilliant. Thank you very much, Andy. Thank you. Excellent. Okay, so we have one more talk for this first session, and it follows on really nicely with Andy's talk, and it's implementing AI in clinical practice and organizational perspective by Leah Strom. And Leah, thanks to an academic background in international economics and innovation management, Leah gained a deep understanding of societal change processes and the need for responsible innovation practices. And for her master thesis, she researched the implementation phase of innovations in the health sector. Her current work at Ethics Lab for Innovation Ethics focuses on creating practical tools for ethical innovation, especially in the design and implementation of new technologies, products, or processes. So you're welcome to join us, Leah, if you're available. We do.
Yes. Can you see the screen? Does that work?
Yes, we can.
Perfect. Well, welcome everyone. So I'll speak about two kind of separate types of works that I've been doing over the last years, but they're also related. So I'm trying to bring them together. And that is the work that we're currently doing with my current company, which is Ethics. We develop in all different kind of fields, so not limited to the health sector, but really all fields. Try to develop ethical tools for innovators all around. So looking at design, but also obviously the whole field of data and machine learning, AI, and trying to support actually companies, but also researchers in developing ethical applications of these and ethical products. based on these new technologies. And when we say, or when we speak about innovation ethics, people usually go like, oh, innovation ethics, that seems like a really broad field. But so it's this moral question of what is desirable and what is the right way to act, or how should the world be organized. So that's ethics in a nutshell, basically. And when we look at innovation, we're usually interested in three levels, on 3 levels of questions in that context of innovation. So we first have all the ethical questions that are linked to technology. We also have, on a second level, all the questions that are linked to the broad diffusion of a technology. So the implementation, which is something I'll speak about more in detail later.